this case, I run the mic. It's not a problem. But
Yeah. And I can repeat questions too if you need to. That's fine.
yeah, it's more for the AV.
No, no, I know.
Yeah.
So I would repeat the question if someone disagreed with it.
Yeah, yeah,
I
yeah.
tend to do that anyway,
Yeah,
so
I mean,
I know what you
yeah,
mean.
I know it's a tough app. It's just
Yes.
one that we should not have to do.
I know.
Two and a half the time?
Did you want me to start like right at or give people a couple minutes to plug?
No, I would start right at schedule just in
Tight.
case there's any problem.
Okay.
I'd rather not.
Let's just keep tight ship. Set the precedent.
Okay.
Okay.
Okay, currently I'm the missing student volunteer, so yep. All right, we are good to go. All right.
Ready to go?
Yep.
Okay. Hi. Welcome back from lunch. I'm really excited to be here. So I'm going to talk to you guys about building scalable stateful services. So like heads up, this is not a programming languages talk. This is more systems based. So it'll be something a little different. I'm Caitie McCaffrey. I am an industry person, and I'm also a systems and distributed systems engineer. I've spent my career building large-scale distributed systems that sort of power entertainment industries or social networks. So I spent a lot of my early career building video games for the Xbox. And most notably out of that, I worked with a team at Microsoft Research to productionize a distributed actor framework called Orleans. And we built all of Halo 4 and the future Halo games on top of that. Most recently, I've been at Twitter working on observability as the tech lead, and then I recently just switched to building distributed build systems, so all really fun things. I'm on the internet. If you would like to talk to me, please do that. I do that. My DMs are open on Twitter if you have like a question or something afterwards, if we don't have time. I also wanted to just point out, since this is a nice bridge between academia and industry, that I'm also associated with a group called Papers We Love, which tries to do this as well. Papers We Love is super awesome if you don't know about it. There are chapters around the world, and the idea there is we have meetups, generally monthly in some of the bigger chapters, to talk about academic research and facilitate discussion there. And I'm in the San Francisco Bay Area chapter, and so we have a lot of good hybrid and discussion going on. So I think that's also a really amazing group. And there's a conference in St. Louis in September if you want to come. Okay, so let's get started. So we've been building systems in this world of the stateless service paradigm. So this is sort of like the idea that everything's like horizontally scalable, and so when I get more users, I just add another machine, and this keeps happening, and then things just scale, and that's okay because either our workloads are partitionable enough that they can easily be parallelized, and you have concurrency problems, and so like typically that's been fine. But the implicit assumption here is that basically we're assuming that our data storage also scales, and that's actually non-trivial to do. And so we're sort of hitting this world where maybe this is also a little bit slow and doesn't meet our needs. So this paradigm basically relies on the data shipping paradigm, and the idea here is a client comes in, it makes a request, and then it'll go to the database or whatever your caching layer is. It'll get that data, pull it onto some machine, which will then process that data, and then send some use to the client, and then that data gets tossed after the end of that request. And so either via like explicitly memory managed or cleaning up memory or via a garbage collector. And so then the next time a user comes in, and we have very chatty clients these days, comes in and makes a very similar request and needs the same bit of data, it's going to go pull it from the database, and it's going to answer that request, and it's going to throw it away. So this is maybe wasteful depending on how your application behaves. It's very wasteful for things like mobile games. It's very wasteful for things like, so all the apps which are very like user-centric these days, a lot of times you're operating on the same set of data, and you have these sessions that are long-lived, and so can we do better? So the idea here is we're going to talk about maybe how we can do better, and this is actually an emerging trend that's happening, building stateful services. This is not databases, this is not caches, this is actually having state in our services, and I'm not going to talk about replication, this is basically focused purely on data locality and some of the latency benefits we get there. But a lot of people are doing this in industry, and so I think it's an interesting problem because I'm going to walk through the model of how we build this, but I think it's maybe something that could be solved at a lower level with a better level of abstraction, so I think that's an interesting conversation to have in this venue. So we're going to talk about some of the benefits of this, like why are people doing this, how are people building these systems, some real world examples so that you understand just the use cases and where this is actually happening and working and whatever, we're just doing it in industry, and then some of the pitfalls and side traps that people are falling into there. So the biggest benefit of stateful services is this idea of data locality. And I think that's pretty obvious, right? Like, if you have data in one place and you don't have to go pull it from the database every time, then that saves a lot of latency. So for instance, in the team I'm currently working on, we're doing distributed build, and so like taking advantage of data locality is really huge because we have a mono build at Twitter, so if you have to pull the diff down and like sync that to a machine and then you just throw it away after you run like one test case, that's pretty wasteful. So we want to take advantage of data locality. Same thing in Halo, when you were online and you're doing something and you're very sort of narcissistic as a Halo player in terms of how you interact with our services. You're constantly asking questions about yourself or like what you're doing or what are my stats or what are my teammates doing, and that's all very session-based data that is being operated on, and we wanted to respond very quickly. So data locality revolves around the function shipping paradigm. This is just the idea that I move the function to the data. So in a real world system, what actually ends up happening is you have these services. I probably still have a canonical source of truth that is the database storing all this durably for me. But then when I make a request the first time I start a session, I will pull that into some machine. And then every subsequent request, I will just keep going to that machine. And so then I don't have to keep going back to the database, and I save some round trips, and I save some load on my database as well. So that's super nice. And then you just figure out how to clean that up later when the session ends, and usually a timeout is fine for that. Okay, so the way we build this is this idea of, or one of the other benefits is that when you build these sticky connections or these long-lived connections to a machine that has the data that you're on, you get some different consistency models. So just to sort of like quickly define, I think it's clear, but like a sticky connection is just I'm always going to talk to the same machine in the cluster that has my data for the length of my session state. This is a diagram that I borrowed from Peter Bayless about consistency models, and so like I don't want to like harp on CAP because I think it's not necessarily the most interesting model, but the idea here is that a lot of things that are considered CP and non-available when you have just generally like no sticky sessions can actually be made more AP, and you get easier consistency models that are easier to reason about, I think. Werner Vogel made this point from Amazon in a paper in a blog post in 2007 where he talks about eventual consistency, and this is around the Dynamo paper, which is their key value store. And he basically says that like stickiness is this idea, or that you can get stronger levels of consistency with stickiness, and it's sort of a nicer model to program for the developer, because if you think about it, it's logically easier for me to think about as a client-side developer, which is clients are part of a distributed system, to say I'm always sort of talking to the same machine for the length of my session. I don't have to think about all these race conditions and concurrency issues that can result because I'm talking to a variety of different machines. So that's sort of where all of this started, or this terminology came from. Okay, so how do we build sticky connections to take advantage of this? So once again, we're just trying to do this thing where we talk to the same machine in our cluster every single time. And there's a multitude of ways to do this, and then I've seen this done in industry, and there's different trade-offs and problems that come with each. So persistent connections is honestly the easiest, dumbest thing you can do, and it's the way a lot of people start. I mean, this is why we have streaming protocols, right? So this is just that like when you start a session, your client's gonna open up a persistent connection, whether that's TCP or like pick your protocol, like HTTP long polling or Speedy, and you're just gonna talk to that machine just because you have a pipe open, basically. So this is easy to do. It's problematic because obviously once the connection breaks, you lose any advantage that you had, and that happens very frequently with mobile clients since they go on and offline and lose service pretty easily. It's also problematic in the sense that if that machine, like if you're just doing like round robin load balancing and it just connects to any single one, you're also making this implicit assumption that the services or the request in every client is basically the same amount of load on a server. In reality, that like 100% never happens, and there are some that take up way more load than others, and that's okay because that means like some people are just more active users of your service, but if you don't build in back pressure and allow your service to make or break these connections and say like, hey, I'm overwhelmed, you will actually just see cascading failures throughout your cluster. So you have to build some more stuff in to make sticky connections work at scale and not just take down your cluster and be unreliable. The other option, if you want to get a little more advanced, is routing logic. So when you do routing logic, it's just this idea of I talk to any machine in the cluster to sort of start the connection, and then it'll send me to the machine that I want to talk to. And this is definitely more involved, and I sort of break this down into two problems that you have to solve. There's this idea of cluster membership, like what machines are in my cluster, and then work distribution. How do I determine like which machine in the cluster gets assigned to this session or this workload? So like cluster membership is pretty simple. There's either static or dynamic. Static is obviously easy. It's bad for a lot of reasons because if you have a machine outage, you basically have a partial service outage because anything that was getting routed to that machine can't get routed anywhere else because you have no dynamic way to update your cluster membership. It also just means that you have downtime to add capacity. So in the real world, this is like, or in industry I should say, this is generally not acceptable anymore. Having downtime is generally seen as like pretty bad and embarrassing, and if you say like, if you put up a like we're down for maintenance page, people like definitely pick up on it and they're like negative press headlines. So this is sort of not really a solution for most highly available user-driven systems today. The other one that's obviously more complex is the dynamic cluster membership. So this is more fault tolerant because just as machines come and go in my cluster, I can add them and they can start doing work, and then as like one goes away, it's fine, it'll just rebalance the load. So that's more what we want generally. And so the way we can do this is basically there's another choice here, because sort of one of the fundamental problems with distributed systems is there's always a trade-off, so there's no perfect solution. But we either start with gossip protocols or consensus systems. And here the choice you're basically making, once again going back to the CAP theorem, is this idea of availability versus consistency. And what do I care about in my cluster membership protocol? And there's different decisions that we'll walk through, like why you might make this decision. So consensus systems are just this idea of like an industry that's like Zookeeper or etcd, and then like like the algorithms underneath are either Paxos or Raft or Zab. And these are just pretty standard things that everyone uses. People use them for service discovery today. That's sort of like what we're talking about. It's not anything super fancy here. Gossip protocols are more interesting, or like epidemic protocols, and I think this is a super nice thing to think of. And like, once again, I want to point out, like, none of this is new. Like, obviously, consensus systems have been around for a while, and gossip protocols are also used in a lot of NoSQL databases. But basically, gossip protocols are nice because they assume non-reliable networks. They use like information dissemination techniques and pairwise communication. And this is just sort of an easy walkthrough of what's going on, but basically they'll start up with no state, and then they'll sort of communicate with each other to figure out like who all is in the cluster. And they'll just do this by sending pairs. And there's, this is the most basic form of this. There are more optimized versions so that you can minimize network traffic and stuff like that. But the idea is, at the end of the day, everyone in the cluster now knows who everyone in the cluster is, and so they all have a consistent, or they all eventually will converge on a consistent view of the world. But obviously, as that was going through, they didn't have that, and so that could be problematic if you need really high levels of consistency in terms of like how you're doing work distribution throughout the cluster. Okay, so work distribution is another idea of how we do these, and I think there are different trade-offs along the lines of each, and this is the idea of, now that we know who's in our cluster and I get a request, like how do I assign it to that machine to do the work? This one sounds super dumb, but there's actually a real-world example that does it very well, and so I talk about it a little bit, and it's random placement. So maybe this isn't directly sticky, but it is this idea of we're keeping everything in memory. So I get a request, I write it to anywhere in the cluster just via load balancing, and so what this means is that when I read it back, I have to read from everywhere in the cluster. So this is kind of, seems silly because you're like, I don't know where anything is, but for very high write workloads, this is great. And then when you have read, generally if you're doing a very expensive read query, you have to fan out throughout the entire cluster to read it anyway. Or you're pulling in a lot of data. This is really nice because it automatically sort of like parallelizes your reads. This consistent hashing is another pretty standard way to do workload distribution, and this is used in a ton of databases. It was I think it was like first talked about in a paper in 1997. It was used for distributed caching to relieve hotspots on the World Wide Web, and then Dynamo obviously made this very popular when it was released, as it uses it to figure out like where shards work. So basically what's happening here is that you essentially hash your nodes in the cluster to the same space as your requests. And so these big, like, solid colored nodes on here are basically our servers, like node A through D, and then the little ones are requests that come in, and they get hashed onto the same hash ring, and so basically wherever it falls, you just walk right, and that's the node that the request gets to. And so what's nice about this is, unlike a hash where you would just take like a normal hash, when you remove a node from the system, it's not like you have to reshard everyone and move everyone around again and all the requests, because that's very expensive. Like, so if node C just failed all the requests before, it would just get load balanced to node D and things like that. So you are doing a minimal amount of resharding when nodes fail or when they come and go. And so that's really nice. One of the problems here, or maybe it seems, so this is deterministic placement, right? Like, I always know where a request is going to go given a stable view of my cluster. This seems really nice because you sort of like can just calculate anywhere where a request is going to be and like what node it's going to be on. But it's actually fairly problematic because once again, you're making this assumption that all workloads are exactly the same. And that also rarely happens, especially when you're talking about like running a query on a database. So you can get hotspots, and in practice what this means is you run these clusters with a large headroom of capacity to be able to handle the fact that you have to run at the max hotspot, right? So that's less cost effective, I think. Another way of doing this is a distributed hash table. This is pretty easy. Obviously, you just come in, and then I'm gonna, like, the first time you come in, I'm gonna hash and figure out, like, hey, you should talk to node A, and then the next time it happens, that's fine, and you would talk to node A, but the nice thing is because it's not deterministic, and I'm just keeping a hash record of where I'm routing your request to, I can update that on the fly. So that allows me to write a program that alleviates hotspots within my system, and I don't have to do that, or I don't have to like run at this extra headroom because I can just move stuff around should it become too hot on one machine. Okay, so that was sort of a lot of information, so let's put it into practice. How are people actually combining and using these things in the real world? So Scuba is this system from Facebook. It's basically how they do a lot of their real-time analysis and queries of metrics and debugging, and they can go and ask questions, and this has sort of been very, very widely successful for them. And they use this fan out on write, and they write randomly, and so then when they read, they actually go to every single machine to ask data. They run the query on every single machine in the cluster. And so, like, this may seem silly, but it's actually really nice because generally the data that they're pulling in is very large, and so then they just, like, parallelize the reads out, and then you're not just, like, totally swamping one machine with a very heavy workload. And so this could be problematic in the sense that if one machine goes down, then obviously you're missing data. So what they do is they just say, we'll return the results we have and a correctness value of here's the like percentage of data that I think is here and correct, because we can basically say with a normal distribution of machines, if one is down, then we know that we're missing this much data, and then the user can make the call of, is this enough consistency for me? Is this enough correctness, I should say? Is this enough correctness for me to make a decision? Or do I need to like wait and run this query again and try and get a better, more correct view of the world? So I think that's actually a really nice real world solution to this problem. There's a paper on this as well that you can go and read if you're interested in more Scuba. Uber Ring Pop is this thing that Uber developed. It's in Node.js, and they have this problem of when like drivers and riders are going around, you have your phone, and it's very chatty, and it's also a session state that's like has a or it's not deterministic, but has a time in which you are being very chatty with their services. And they made this observation that like, hey, it would be great if I didn't have to round trip to the database every single time that I wanted to update something, because that's slow and that's a lot of load on their database. And so they put everything, they wanted to take advantage of data locality. So they went and implemented routing logic, and they used the Swim Gossip protocol, which is a paper that came out of Cornell for cluster membership. And this is actually a pretty popular way to implement Gossip in industry. It's one of the more the favored ones. And then they use consistent hashing for message routing. So when you have like a session ID and you're always routed to the same machine. So one of the nice things about this is they take advantage of data locality. This is open source on GitHub if you actually want to go look at it or try it out. One of the problems they actually do have, though, is that because you have a consistent, or because you're using a gossip protocol for cluster membership and you can have a partition in your network, then you could have split brain mode where some of your requests from your phone are going to like one side of the partition and the other are going to the other, and so they have to write code to handle like merging all that state back or dealing with that. So that's nice, but it's also nice because then there's basically no time at which like Uber will be like, sorry, like I can't, like too many nodes are down or whatever, we have a partition and you can't get a ride. And so Uber and a lot of businesses choose availability over correctness and will deal with the consequences later and fix it up because like if you can't get a ride with Uber, like you're more likely to pull open your app or your phone and look at another app or stop using them, and that's bad. One of the other problems is obviously this has deterministic placement, so if for whatever reason you get a hotspot or a hot shard, there's nothing you can do besides add more capacity. Okay, and then I want to talk briefly about Orleans because I think they do this in a really interesting way. This was a project that I was involved with. So Orleans is an actor model and a distributed runtime that came out of the extreme computing group at MSR. And so basically actors are stateful services because actors can, they're basically little state machines that run, and they can receive async messages, and they can create new actors, and they can send messages, but they can also have their own internal state, and they can modify that. So every time you make a request to Orleans, an Orleans cluster, it'll route it to the right actor. And I'll talk more in depth about how we do this next, but I just wanted to mention that Orleans is available open source on GitHub, so you can go and play with it today. And there's a paper, and then it's also like the core tech that we shipped Halo 4 and 5 on. So this is like a very real-world system that works. Okay, so how Orleans does its routing, I think, is actually pretty interesting and allows Orleans to do a lot of the magic it does. So it uses a combination of basically like a gossip protocol to propagate the cluster changes. It actually uses a more consistent store, either Azure Storage or Zookeeper or whatever your plugin library is, to say like these are the nodes in the cluster. But then it is an eventually consistent, like the model, all the nodes knowing who is in the cluster has to converge because they use a gossip membership or protocol to propagate those changes out. And then they use a distributed hash table as well. So what is actually happening when you make a request to Orleans is you come in, and it's going to say, like, for instance, in Halo, we hashed on your player ID a lot. And so we look at your player ID, and we would say, okay, do a consistent hash on this person's player ID. And that would tell us where in the cluster your information you're entering the distributed hash table was. So you have to do a hop. And then it'll eventually route you to the machine where like your actor is running, and now like you're good to go, and like you can run whatever computation you had to run. And so conversely, like if you came in on another request, you might go to another machine, and say for instance, like this is a couple days later or whatever, or there was a failure, and so your actual state, your actor is moved to another node in the cluster. Your consistent hash or your distributed hash table lookup is still the same because it's a consistent hash. And then you're going to get routed to wherever your node happens to be. So I like this pairing because an actor reference, basically, or where the machine lives, is basically the same for every request because it's just like 80 bytes of memory that says like this is like the user and this is the machine where it lives on. So that's actually the same regardless of like the load that our user is going to do. So there's no hotspots or deterministic like problems with deterministic placement here. And then because they can actually move these things around when you get a hotspot and it's a distributed hash table and non-deterministically placed where your actor runs, it handles failure very seamlessly because if a node goes down, then it'll just like it'll just remake it somewhere else. And it also allows Orleans to do really nice things. Like if one of your machines is running too hot, it'll just move nodes, it'll kill nodes on it and just move them somewhere else. And there's nothing wrong with that. And that actually works really nicely in practice because we ran the Halo services at about 90 to 95% CPU utilization in production. So that's really cool because you get to use the whole box. So I really like this method of how Orleans sort of distributes load and does that seamlessly for you. Okay, so what are some of the challenges associated with stateful services? This is sort of, I mean, it's like a new paradigm for web developers, right? Like database people and cache people have been doing this for a long time. But there are some gotchas if you haven't been exposed to a lot of this before. basically, you now have unbounded data structures, and like you did in stateless services before, but they only like lived for the length of one request, and now they could live very long terms for like, you know, minutes or days or hours. And that could be problematic because if you don't make your assumptions or explicit in a distributed system, it's generally going to cause a really bad time for someone down the line. So the canonical example of this is that people do this with distributed queues in distributed systems. You'll sort of hear that, you know, all these horror stories about, from Twitter about like how we had the Ruby on Rails monolithic app, and then we used queues for to do RPC, and then the queues would back up, and the unicorns would get sad, and like all these horrible things would happen, and Twitter would have outages. And that's just basically because we were assuming that like our queues were unbounded, and like nothing's actually unbounded. There is a limit, you just don't know it, because machines have real memory. And so the same thing sort of happens with stateful services. Another example of this is at Twitter on observability, we have an indexing service that's like basically all in memory, and we sort of just assumed when it was made that things would, the number of metrics someone was indexing per service and how we were doing this would, you know, be a reasonable size. Whatever reasonable happens to be. And then the observability service at Twitter grew by an order of magnitude, going from hundreds of millions of metrics ingested per minute to billions, like on the order of 2.8 billion. And growing by an order of magnitude exposes sort of all these implicit assumptions that were made, and so that service used to struggle very hard because some services were adding tons of metrics and it would blow out memory, and so we had to go and add some explicit bounds and help people partition their data a little better. So starting with this idea of, you know, making implicit assumptions harder to make, actually is a really, like forcing people to do explicit assumptions is really good for making reliable distributed systems. Another thing that's a gotcha and seems really obvious, but a lot of people don't think about it until you get into the depths of these, is memory management becomes a problem. Garbage collectors are not really good at dealing with long-lived state, typically, at least not on the JVM or C# side of things. We ran into this problem at Halo, where our statistics service, which does all the aggregation of your stats per player and is long-lived for however long you happen to be playing Halo Online, you have an actor running in our service, and like just your session state, it goes away like once you log offline. But it could be hours. Like people played Halo at launch for like days straight. It was crazy. And during a tournament, they played it for like 48 hours straight because we were like giving away a truck or something. But that's like a whole thing. So anyway, the C# garbage, or the CLR garbage collector got very sad. Because it's like, hey, you're storing all this state in memory, and and depending on how your garbage collector is implemented, so I know a lot about how the C# one was, because we had to tune it, and you had all these references going around. We had to go and tune that and sort of make friends with our garbage collector and do some object pooling and things like that. So that does get harder when you have these long-lived things. So, you know, an interesting question is like, if this becomes more important going down the line and people really care and want to build more stateful services, is there a garbage collector that is optimized for long-lived objects? Basically, I haven't seen a lot of research in that area yet because people don't really do that all that often, and then like databases are written in native code a lot of the time, although more are being written in Java, and it seems to be okay. So we should talk about how they're doing that. The other interesting thing here is that once you reload state, from like a user perspective, I don't want anyone to know in the background that I have like a stateful service. I don't want the first connection to be really slow. Or in the case of when a failure happens and then we have to spin up your actor or your state on another machine, I don't want that to appear really slow in timeout. It should be kind of transparent to the user what's going on. So you have to be really careful about when you on boot, when you reload state, you want to only load the minimal data set on restart. Another interesting thing is that if it fails, you should keep loading that state because there's like a timeout or something, because they're probably going to come and ask you for it later. And that's totally different than, you know, you cancel everything once a stateless server request fails. Another really interesting thing that happens in industry is that typically, you know, adding capacity or like replacing nodes is not super all the time. It doesn't happen that often. But deploying new code actually happens really frequently. And so if that is really expensive because rebooting the entire system with all this state is noticeable to your users, then that slows down your development team, and that's really problematic. So Facebook actually ran into this problem with Scuba. So they published this paper that I actually thought was really cool because it's not a hard concept, but it's just like this key observation that was just like totally paradigm shifting. And what they did is they found that restarting all the Scuba nodes and to deploy new code like took them like 12 hours or something. So developers literally just sitting there babysitting this deploy for like 12 hours because of how slowly they have to roll the cluster. So that's awful, and like no one wants to do that. And it also disincentivizes your team to ship code really fast, which is bad. So what they did is they made this key observation that basically, so Scuba's written in C++, I think, or C, one of those. They manage their own memory, and they decoupled the memory lifetime from the process lifetime, right? So we know that memory is bad when a process crashes, and so obviously we have to basically reload everything from disk or some durable storage. But when we're doing code deploys, which happens way more frequently usually than a process crashes, or you hope to get to that point, the memory is good, so we don't have to throw it all away. So basically what they did is they copy all the memory that's running into shared memory, and then they kill the old process, and then they bring up the new one, and then they copy all the memory back. And that took like 2 to 3 minutes instead of 2 to 3 hours per machine, and so deploys took like 2 hours, which is really cool for this simple trick. So it's sort of, when you start thinking of services in this way, it sort of is very, it's worth reevaluating a lot of assumptions about like, oh, well, like when a process crashes or like when you have to restart a process, you can't trust memory. And they published a paper on this that I'll link to in my references section at the end. So like sort of in summary, like data locality and availability are like very big concerns from an industry perspective. And like as we went through, like there's all those choices that you have to do, and that's actually a lot of code to implement, and it's actually fairly challenging to get right. And I think there have been a lot of successful real-world systems, which means this is going to keep getting adopted as a solution. But it's hard, and so like, can we think of better abstractions? Can we have better runtimes or programming languages that maybe do some of the work for us? This idea of, you know, moving state around in a system is not new, right? Like it's happened in other papers like Emerald and things like that in the past, and so maybe that's an idea worth revisiting, that we bake this into a language somewhere so that we can just have all these advantages and not everyone has to write all this messy code that's easy, that's time consuming to write and easy to get wrong. Okay, so I want to take questions. I also just want to point out I have a repo up on GitHub if you want to, about all of the papers and things referenced in this talk or any of the links, and the slides are also up there. So if you want to do that, check that out. So thanks. Hi.
Are you aware of any practical real-world problems of using consensus for membership? I mean, it should be, the protocol should be pretty rare, and why would that be a problem?
So using consensus for membership is problematic if your consensus system is down. It's also problematic in the sense that like, what you have to make a decision then to say like, either I totally kick out nodes from a cluster, and then like the state gets smaller, or like how do I, like what if like some nodes are partitioned from the consensus system and they're off doing stuff? How do you, it's a non-trivial problem to solve, and the option basically is like you stop serving requests at that period in time, and that's generally not a solution that like your business partners will tolerate.
No, but are there cases that more than half of the machines actually fail in a cluster?
Most industry clusters cannot survive half of the machines failing that I know of. Because you don't provision that high. I mean, some can, like at bigger systems, but most people do not run it with that much elastic capacity that I have seen. And so like, so for instance, like with Uber and explicitly at Halo, we made the choice that we always want you to be able to talk to a service, and we will take the problem of serving you stale data and deal with the consistency problems that generates, versus you not being able to talk to, have a ride scheduled, or be able to see your statistics or play Halo, right? Because that was just mission number one, is you had to be able to do the thing that the business wanted you to do.
Thanks.
Hi, thank you for the talk. Can you give more details about how the state of an actor can survive a crash?
So Orleans doesn't, so I'm assuming you mean in Orleans, right? Okay, so Orleans actually doesn't do anything along those lines right now. And the reason, I don't know if people are familiar with Orleans, there's actually like a couple papers that are not like what I call Orleans canon, because they were like ideas, and then we started working with them where they were gonna try and do this like whole transaction model and like rollback and detect when there was a consistency violation, even in the super available world, and then like that problem's actually really hard. So I don't think it's like totally abandoned, but what we cared about was availability. So what we did in the system, and the reason they didn't want to do it, a generic solution is actually really, really hard. So, because there's a bunch of different options. So for some services, we didn't care if we persisted state between activation because like it's a heartbeat service, or our present service was telling you what you're doing right now, and you're gonna talk to me in like 30 seconds later, or like a second later if you have a connected device, and so like if I lose that data, no one cares. Statistics, we actually had to persist that, and that was one of the more complicated systems because that also had to be very correct. You couldn't double count things. So you had to persist. We treated them like write-through caches and then detected inconsistencies in case you were in split brain, and then did a whole bunch of other stuff that I can talk about offline on how to deal with that. And then some things are like, some services may want to persist, periodically, like just checkpoint state. And so right now there's like a bunch of, I believe with Orleans, there's actually a bunch of open source code on like how you can do a bunch of different, or patterns on how to do this, but they sort of leave it up to you as a user. And I think last time I talked to them, they were investigating how do you use like CRDTs with Orleans, because that would be actually a really nice solution to this problem if you don't have, like you always have mergeable state, right?
Hi.
Hi.
So what do you think, so kind of the key assumption is that the database layer or the storage layer is slow.
Yeah.
So what do you think of something like Ceph for distributing on the database layer instead of adding all this caching to the logic layer? Like,
so I don't actually know Ceph, but I'm assuming it's something along the lines of the fad now, which is like everything's part of the database.
So Ceph is, it's a storage layer, so it's basically like disk, but where the clients can go to any node in the cluster. Like the clients can figure out where the data is.
Yeah.
So there's no central point.
So it sounds, so this is doing like sort of that, except for like I still have a database. The reason a lot of the times people do this in industry right now is then you don't have to deal with a lot of consistency problems. Because if you notice, I wasn't talking about replicating data, and we didn't in any of this part. We just relied on our storage systems, replication, and fault tolerance, and also some consistency. You run into a lot of really nasty consistency problems, which is why just throwing a cache in the middle also honestly doesn't work a lot of the times, because once you start having concurrent access, it becomes problematic. And then one of the things that Werner Vogel pointed out with the sticky consensus is it's very easy to sort of reason about like, and a lot of the ways these actors are implemented, or actor models, or some of these systems, like the Uber ring pop is in nodes, so there's obviously only one thread, and you don't have concurrent updates to things happening. So you just get to write simpler code that doesn't have to deal with concurrent modifications on your data.
Oh, and the other thing I'm wondering is, what do you think about Erlang as a language that kind of integrates distributedness in the language?
So I think Erlang's actually really cool. So I don't think I pointed this out, but I'm super polyglot. I've programmed like 10 languages in production, so I'm like less any one language versus more of there's just tools. I think Erlang's super cool. Obviously, like Orleans building on the actor model is drawing a lot of inspiration, or whatever you want to call it, from Erlang, or building upon that knowledge. Orleans makes a nicer, like, or they have a programming model associated with it that's like has types and interfaces and stuff, so it's a little easier than like sending something to Erlang and then it blows up because like it doesn't accept that message. And then Orleans did a runtime which obviously like helps you distribute the stuff, which is also run the cluster, which like the Erlang runtime has that as well. I think the actor model is actually super powerful for building distributed systems, and I don't think it's, in industry it hasn't gained as much adoption as I would like. Orleans and akka have some widespread adoption in their various communities, and like obviously Erlang has adoption as well, but it's by far not the most prominent paradigm, and I'm not sure like why. I think it's really great.
Hey, yeah, in Elixir there's also Gen Stage has been introduced recently, which is quite interesting for back pressure.
Yeah, Elixir's cool too. I haven't played with that one as much, just because I haven't worked in like an Erlang or Elixir shop, but. Anything else?
Do you think that for implementing such generic solutions, you always need help from the virtual machines? Or can you think of systems that like are generic and work across a number of programming languages or virtual machines?
Oh man. So I have yet to see one that works across like any kind of language right? Like everything's sort of like either built into the language or as a runtime. Like Orleans at least works with like C# and F#, and I guess like Akka works with like Java and Scala, but that's because it's like it's like they're all still like sandboxed to the CLR or the JVM. I don't know what that would look like to be able to like compile down to multiple things. Way out of my domain of expertise. Anything else? Cool. Thank you so much.